this is kind of exciting, and she brought with her Lindsay Fuoco, who is working for a little company that many of us don't know exists. You've heard of L3 Harris, and most people think it's just on 7th North, where they do a lot of the satellite stuff, but they've got a facility doing a lot of piezoelectric and some other ferroelectric work right here in Salt Lake City. So Angie Richardson, right here, she graduated in metallurgy from Minnesota, and without a Utah connection, she ended up in Idaho. And INL, I guess, wasn't good to her, so she came down to a company called Ceramic and was able to see that there were better things other places, and she ended up with a company called Idaho Western. Idaho stands for the three initials Evan Dodge Osborne, who founded an aircraft company in the 1920s. And they started making platoons for airplanes. But in 1950, they located in Salt Lake City, working with government contracts for the Navy on sonar and other ultrasonic transducers, and started a work that continues to this day. The company's now owned by L3 Harris. Angie was there for 28 years, and during that time, she led all the operations work for making the devices. There's a bunch of electrical engineers who are also employed there. And then she went off and worked for another ferroelectric company, and eventually realized that she could be more successful as a consultant, and traveled the world and was involved with a company in Israel making devices that end up with cancer treatment. So it's really cool to see where things have gone. It's been 40 years since I've seen, well, almost 40 years since I've seen Angie. And Lindsay is also someone we've imported. We love imports in Utah. And Lindsay came, and she got her PhD in North Carolina in solid-state chemistry, and ended up doing a postdoc at Northwestern in Argonne. And then she was doing that on batteries, but she saw a position at Idaho for a principal investigator, and she came and took that job, and she's been there for 7 years and does lots of things. And so we are delighted to have them teach us about piezoelectrics and a whole class of materials that almost is everywhere. Whether you know it or not, you're using these type of devices. So let's give a big round of applause to these two speakers.
Okay, can you hear me? I can usually project without a microphone, but yeah, I appreciate having that option available to me. Once again, thanks Raymond for inviting me here. I'm primarily retired now, but in my previous career, obviously, I worked a lot on the nuts and bolts of manufacturing ceramic, and then became a consultant also in that area. So today, I'm going to go a little bit over some of my thoughts on myself and a little bit on what my philosophy is. And then we'll go into some of the piezo technology overview, some applications, and then I'll spend a lot of time on the current manufacturing process. Then talk a little bit about other things that go on in that manufacturing world, and some closing statements, and turn it over to Lindsay as she talks about some of the next generation and emerging technology. So a little bit about me further than what Raymond's already told you is I graduated in the early 1980s. Now you can imagine that there wasn't very many women engineers at that time, so probably less than 5%. I enjoyed problem solving, I enjoyed math, I enjoyed science, and so it was kind of an evolution where I headed into engineering. Then when I graduated, I had the opportunity to go to the National Lab. I did some research there. And when I moved down to Salt Lake City, I really found my niche more in manufacturing. It's fast-paced. There's always problems to solve. And that's kind of what led me to that direction. I had a lot of good mentors, both men and women. And then, I think some of my keys to my success in having a long-term career was that you really, know your topic. And if you don't know, look it up. Look up information. If you still don't know and don't feel like you're an expert in that area, then you need to get someone on your team that is. I worked with a lot of diverse people over the lifetime of my 35, 40-year career. And everybody's a little bit different, but they all bring something to the table. Then the other thing is confidence. I think one thing I would stress to all of you going out there in industry is to have that confidence in yourself. Once you know your topic, take that confidence with humility, because you need to acknowledge that you don't know everything, but take that confidence forward, and then you'll get your voice heard. And then integrity. Trust is so key out there in that industry. So between your suppliers and yourself, between your coworkers and yourself, between your bosses and yourself, you need to have that trust. If you don't have that trust, people are not going to want to go to you specifically to execute, their next contract or hire you at their next job. So I just have a very few slides in piezoelectricity that I just want to talk to here. I think Raymond said that you guys have already kind of heard a little bit about that. So piezoelectricity, basically, it's the ability of the piece of ceramic to generate a voltage when pressure is placed on it, or in contrast, if you put compression on that ceramic, you'll generate a voltage. Discovered in the 20s and the 40s, and those first initial materials were pretty basic, and they really couldn't handle pressure, temperature. Can you imagine being out in the ocean and having your device basically break down because it's warm and your Rochelle salt or your ADP, ammonium dihydrogen phosphate, is starting to dissolve? So in the 1940s, 1950s, a lot of smart people went ahead and developed the polycrystalline ceramic material, which is primarily used right now out there in the industry. And those materials were barium titanate, and then the lead zirconate titanate material. Ended up being commercialized, and then from now, and Lindsay will talk about this in more detail, but the next generation materials in piezoelectricity are tending to be single crystals, lead-free. Everybody wants to get the lead out of their product, and textured materials. So when we think about piezoelectricity, what we think about is a ceramic structure, that perovskite structure that basically is of an AbO3 configuration. So you have the lead on the corner of the lattice, you have the oxygen in the face centered, and you have that zirconia in the center. And it could be titanium too. So the reason you have the ability to create a voltage is the movement of that zirconium atom. Okay? So that zirconium atom, you can add other dopants to this constituent, but basically that there's, depending on what materials, what additives you add to that crystal structure, you'll get different electrical properties. Okay? Within that ceramic structure itself, the way you get to a point where you have that polarity within the ceramic crystal overall is you have these domain structures. And in that domain structures, in an as-fired ceramic configuration, they are random. But when you process piezoceramic, what happens is those domains basically start to align, and then overall you have the polarity of positive and negative. The C position is when that ceramic starts to, over time, logarithmically, it will start to relax. So what happens is that those domains start to want to go back to their original random configuration. And that happens, like I said, logarithmically. So the first 10 days, you may have a certain percent. Then the next 10 to 100 days, the same percent, and so on. Applications. So we'll just talk a little bit about applications before we go into some of the nuts and bolts of manufacturing. Obviously, defense, and Lindsay will probably hit on this a little bit more. So sonar, sound navigation and ranging on manned and unmanned vehicles. So you're basically, what's happening is in this, on a hull-mounted ship, you have about 5,000 pieces of piezoceramic here. And those piezoceramics act together as a transducer, so they're sending out a signal to look for, it could be it could be a submarine, it could be a geological feature that they're looking for. So sonar in general, obviously, is identifying threats. The other devices that typically go on the submarines are hydrophones, and those are primarily listening devices as opposed to projecting devices. And so those listening devices are strings of piezoceramic that get dragged behind, also, once again, listening to what's out there in the ocean. Doppler, piezo is used in Doppler for basically speed velocity and definitely mapping exploration like the Titanic. So, in the medical applications, you see piezo out there in ultrasonic imaging. So anytime you go in there and get an ultrasound, what you're seeing is a transducer device that's sending out a beam, acoustic beam, and then reflecting on tissue and coming back. And most of the transducers in ultrasonic imaging now are actually single crystal, so single crystal piezo. Then also therapy, ultrasonic therapy, endoscopic therapy, breaking up gallstones, and treatments for cancer. So what this device here, is it was developed by a company called Novacure to treat glioblastoma multiforme. So GBM is a aggressive form of brain cancer, and the ceramic works with the field that's being applied to disrupt the mitosis of the cancer cells. So it's something that I was intimately involved in terms of finding out manufacturers, and traveling the world to look into further. Industrial applications, ultrasonic welding, a lot of sensors in your automobile, also in non-destructive testing, so for welds, vibration sensing, oil and gas sensors, flow measurements. It's everywhere out there. People don't always realize that there's a small piece of ceramic in all of these devices that are making them work. And in commercial, you have fish finders, of course, haptic feedback. So when you play a video game and you feel the vibration, oftentimes that's a piece of piezoceramic that's giving you that feedback. Buzzers, like in your watch, micromotors for cameras, and your typical piezo lighter. Now, those piezoceramics that are in all of those devices, they come in all shapes and sizes. And Lindsay was gracious enough to bring some ceramic here. So whether it's at the end of the class or you want to kind of just pass these around, I would imagine these are all lead zirconate titanate, so fairly heavy compositions there. But the larger the frequency, the larger the ceramic, the lower the frequency, somewhere in the 10 kilohertz range, and the higher frequencies typically in the 5 to 10 megahertz range. Unit costs, this is where manufacturing comes into play. So piezoceramic can be only a few pennies or it can be tens of thousands of dollars. And so as a manufacturer, you have to kind of think in that economic sense in terms of what market you're going to be in. From a material process to make the piezo, basically I've outlined 7 different steps here. The first step, inspecting of the raw materials, pretty critical to the quality of the ceramic. So you're starting with metal oxides, lead oxide, titanium oxide, zirconium oxide, barium strontium carbonate, niobium pentaoxide, iron oxide, etc. And then, like I said, those different dopants that are going in there provide different electromechanical characteristics. It's usually an electronic grade of raw materials, which means greater than 99% purity and a very fine particle size, usually large surface areas. Okay. The next, after you've inspected those raw materials, you're going to weigh them, you're going to mix them, react them, calcination, once again, and then mill them down to a fine particle size. I'll go to the next slide. And then dry the powder and inspect it. So what I have shown here at the bottom here is basically some of the industrial type of equipment that you might utilize. A V-cone blender here for mixing of the raw materials, vibra energy mills here to break, can be either used for mixing or they can be used for the milling process at the bottom to reduce the particle size, and then drying. And so drying typically is, can be done by hand, but almost all of the commercial ceramic manufacturers have a spray dryer. In the step of milling here, typically there is an organic binder added, polyvinyl alcohol or polyethylene glycol binder, to assist later on in the compaction of that ceramic. So then after you've got the powder manufactured, then you're going to go through the process, the ceramic process. And we'll walk through each of these steps here. There's just another picture of some more piezoceramic. First and foremost, let's press that ceramic. So we're going to take that powder and we're going to use either typically a hydraulic or a mechanical press to about 10,000 psi. Then this is like a typical type of Dorst press that you might use, a mechanical press. We'll go to a particular pressure. You get a particular size based on the tooling. You might need to check for, what's critical is to check for any flaws in that green state of that ceramic, so delaminations, voids, etc. And the ceramic comes out of there, it's still in powder form, but it holds its shape due to pressure. And so here, I'm sure you guys, you might have equipment that does this. Okay, I don't know if maybe there it goes. So in that hydraulic press, you're basically using a feed right there to fill up, and then upper and lower punches to compress that powder, and then it just gets pushed to the side. Then the next step is, because it's a lead-based ceramic, we need to get some of those organic binders out of that composition prior to our sintering step. And so what you have is you have this binder burnout. Some people call it a bisque fire. It can be done in a continuous or a batch kiln. Usually takes 24 to 72 hours. Pretty critical that you have a lot of airflow because you want to remove some of those organic binders. And once again, it's the key feature there is just mechanical strength. The next step is the densification, the sintering process. With a PZT-based material, you're going up to about 1200 C, and you're processing it for about 24 to 48 hours. In manufacturing, it's so critical. You know, as students, you guys might be doing some firing in small kilns, but when you think about a kiln that is essentially 6 feet wide, 10 feet deep, when it's that large, if you don't have uniform temperature, what you're going to get is non-uniform product. And when you have a specification you have to reach at the end, you could have a lot of waste. And so your yield can be very poor. So it's so critical that you're maintaining a uniform temperature there. And we're talking, you know, like 2 to 5 degrees Celsius within that scope of distance. You can add atmosphere. In the piezo world, we typically might add oxygen as an atmosphere to increase the densification. The components themselves are placed in sagers, typically alumina crucibles, to contain the lead volatilization. So what happens is at about 600 C, your ceramic is going to soften. You're going to start to evaporate lead. Well, if you started with a composition of a particular amount, if you're losing lead to that kiln, what you're going to get is something different than what you plan to create. So 14 to 16% shrinkage, typically watching the grain growth. Obviously, we want some grain growth, but not to the adverse effect of mechanical strength. In the next step, we're just going to do some machining process. Like any ceramic, You typically are using silicon carbide, diamond-based bonded media, and you can use any normal machining centers. They can be lappers, lathes, etc. And then oftentimes you will stress anneal that configuration because you've broken up that surface. The next step is, you probably saw in some of the ceramic that you have, it has a silver paste on it. And that's because we're going to solder wires to this ceramic, because it's an electronic component. So in that electroding process, we're going to apply a silver paste. The paste itself is about 70% silver metal, a little bit of glass beads, and then it's typically screen printed on, but it could be sprayed or it could be dipped, electroplated, sputtered, and then it is fired to make sure that that adhesion between the ceramic paste and the ceramic structure. The next step is polarization. We talked about that, aligning the dipoles. So the ceramic's placed in a bath of high dielectric oil. We apply a voltage to it, pretty high voltage, 40 to 60 volts DC per every thousandths of an inch. So it can be up in the 10s to 20 kilovolts. Then that ceramic is then cleaned and ready for its final test. So when you talk about manufacturing and assuring quality for your customers, most of the manufacturers will do some kind of sampling, or they might do 100% inspection, depending on the requirement and the difficulty of manufacturing that part. Okay, you made that ceramic, but in the manufacturing world, there's a whole nother level of things that you have to consider. Those being documentation. So procedures. There are procedures on how to run the equipment. There are procedures on how to validate the equipment, that it can be actually capable of doing what you want it to do. There are maintenance plans for the equipment. So it doesn't, because you cannot spare to have a breakdown of even one day. So, and then the work instructions for that particular part. So all that documentation has to be done in advance of even making one part. Then you have traceability. You have traceability back to the raw materials. You have records showing all the steps in the operation and who performed them. Guess what? Boeing didn't do that. Think about that panel that came off. They can't even trace back to who did it. And whether it's the FFA or your customer or the defense industry, you have to have those records, and they have to be available like that. So then certainly data that you've taken in your process, in the course of your process. Training, pretty self-explanatory. All your operators need to be trained. Lean manufacturing, another key thing to the manufacturing operation. So I don't know if any of you have heard of 5S before, or reducing waste by looking at the flow. But 5S is just making sure everything is organized. So you go through your factory, every tool is where it should be. Everything is clean. I've been in factories in Europe where, if you're looking at those light fixtures above you and they're filled with dust, guess what? You're going to have foreign objects in your ceramic component. So if you're not considering cleanliness as part of your manufacturing process, then there's a huge opportunity to fail there. Statistical process control, how you sample, how frequent you sample, multivariable testing. Once again, if you have a problem and you want to solve it, to try and test one thing at a time. So, okay, I'm going to test temperature, or I'm going to test a different piece of equipment. If you do that, it could take you weeks and months, etc. Multivariable testing is a way to test all of those variables at once, look at it statistically, and see what is significant, what is causing your problems. Calibration of equipment, obviously, I don't want to go out there and use a micrometer or a caliper and then find out later that it wasn't holding tolerance. So critical. And then the ISO documents, anybody who comes into your facility is going to want to see that you have certification for certain standards. ISO 9001 is pretty standard out there in terms of manufacturing, but 13485 is what the medical industry uses. And basically you're defining how you're going to do a process and then and how you're going to keep your records. When I'm going to finish up here and I'm going to hand it over to Lindsay, but as I look what the challenges are for people going into manufacturing and in the ceramic industry, dependence upon material sources outside North America. You know, I have to admit that most people are getting their raw materials from China and Asia. Is that a problem? It could be a problem if all of a sudden you can't manufacture what you need. I think that the government is very concerned about that with the chip manufacturing right now. Dependence on lowest cost labor. When I look at where I want to make something, certainly places like Mexico, Eastern European, like Romania, might show up, Asia. And those are great options, but once again, you're dependent upon a remote location for your manufacturing. And then automation to stay competitive. If you're trying to reach a price point that maybe is $1 or 50 cents or even 5 cents, you can't do that unless you have put the time and effort into automating your process. Looking forward, I think that Lindsay will talk a little bit about material development, design engineering to how do you use piezo in new devices going forward, and retaining intellectual property. I can tell you that I have worked at companies that where their IP has been taken overseas. And from there on, basically, they've lost their competitive knowledge base and business. So with that, I'm going to turn it over to Lindsay, and she's going to impress you with her next generation stuff. And then we can take questions at the end. So. Okay. Here's the HDMI. Okay. Yeah. Hope you have a HDMI. Okay. And you're okay with power?
Yeah.
Okay. Cool. Here's some more. This is some of the ceramic that was used for in some of the brain cancer stuff. I don't think I put that on, but. Oh, I bet you want this thing. So.
Oh, I don't know.
Oh, okay, okay.
How do I get this to work? Let's see. There's that guy.
Yeah.
did duplicate. Oh,
It took a second for mine to kill him.
there we go. Okay, got it.
Got it?
I think you need that microphone here on the camera.
Oh.
It's just like a recording machine too.
Oh, okay.
Yeah.
Okay. Okay. Good afternoon. I'm just going to touch on some stuff that I do at L3 Harris, Idaho Western. We actually have 2 facilities in Utah. Most of you are most familiar with the one that's over by the airport. It has like 3,000 employees. They do something totally different than we do. They do communications, and I'm primarily going to talk about this facility here, which is located in South Salt Lake City. We're formerly Idaho Western. We've been at this site doing ceramics since 1954. So many years of knowledge. And we're actually one of the largest piezoelectric shapes producer. And when I say largest, we're not the largest company. We make the largest shapes. So, but yeah, we also do acoustic and transducer designs there. We do ceramic manufacturing and design. And then, we're vertically integrated within one facility. So we have a ceramics manufacturing portion, and then we have our acoustics portion. And actually, let me grab this. What I've kind of shown here, this is actually our acoustic test facility there. And that's about, I think it's about 130 by 160 feet by 36 feet deep. And this is where we do all of our acoustic testing. And we actually just expanded this. So I think a lot of people wonder what we're doing there. But yeah, this is quite exciting, and you can actually run a kind of like a tram up there that's going to test some of our larger equipment, that's actually quite large. And then, of course, here's our ceramics manufacturing line here. I've been there for 7 years. I'm actually the textured ceramic manufacturing principal investigator, and then I do a little bit of acoustic engineering and transducer engineering as well. So, okay. So Angie kind of brought up, the next generation of piezoelectric materials. And she talked about 2 things. She talked about single crystal and textured. So when we look at all the materials out there that are available today, what she mostly talked about today is this random polycrystalline. It's going to be your cheapest material type, but it's also performance limited. Because these random crystal orientations, even after you pull it, it's going to, result in an averaging of, your physical properties. And then over here, we have our most expensive, which is single crystal. And this is actually a 1-domain material. So it is pristine. This is your perfect material. And while it is, pristine, it also has some robustness issues. When you're making single crystals, what I'm mostly talking about today is PZT, which is a solid solution of your lead titanate and then your lead zirconate perovskite structures. And for this, it's actually quite hard to grow a PZT crystal of the formulation that you're targeting and have the entire bullion that you're growing to be of uniformity, of the same uniform composition. So that's one of the problems we talk about there with that. Also, it's quite expensive to grow single crystals. To have a facility that makes many of these, you're looking at, to grow this, the whole process, you're looking at a month, just to make this one single crystal. And while it, has these fantastic properties, that's quite a bit of time. And then also, it's usually grown by the Bridgman growth method, which utilizes platinum crucibles, which again, if you're going to grow single crystals, you're going to need to have your own facility to refine these crucibles, and do that as well. So that's some of the limitations. But what I'm going to talk about today is textured, which is kind of this in between. You have properties that are approaching single crystal, but it's lower cost to process. So it's similar to, your polycrystalline typical ceramic materials, but you have this higher response because we're actually engineering domains to almost be like a single crystal. So I'll talk about that a little today. And what I've shown down here is just some properties where you can see here, this K here is kind of your energy efficiency coefficient. So single crystal is going to be approaching 1, and then here would be polycrystalline, and then just here is an example of textured, where we're actually approaching this really high efficiency coefficient. And what this means for us in transducer design is, this is reduction of your overall system size and weight using something that's textured. And we like to refer to that as SWAP, which is size, weight, and performance. And we talk about that, kind of all the time. So what is the process for doing this? Okay, so the first thing you really need to do is grow what are called template or seed crystals. What we usually use is something like barium titanate. These are going to be used to kind of engineer your domains of your PZT material. So when you choose a seed type crystal, you want to make sure that you have minimal lattice mismatch, close lattice constants, close structure. So what I've shown up here is just the barium titanate structure, and what we're looking for is we want something that is highly anisotropic so that we can align it and engineer these domains in the next step. And this is just an SEM image of some barium titanate that we've grown that we call our seed or our template crystals, which are very important to getting this texture process. So once we've grown those, using slightly different than usual metal oxide ceramic manufacturing processes, which I'll touch on in a second, we're going to use something called tape casting. And what we're going to do with that is you have your slurry, which is made up of your ceramic, which is actually most of the content of it. And then you're going to add a small amount, maybe 5% or less of these templates, very, very small. And then you're going to add some binder additives and, a solvent, in our case, water, because it's just more environmentally friendly. And what you're going to do is you're going to tape cast it. So you're going to run it under a doctor blade. Down here is a carrier film that's going to flow through, and your seeds are going to align in this one direction. So here what I've actually brought today, and I'll pass it around. Usually when we tape cast, we have a large roll that's hundreds of feet. And in the second step, we cut this. So this is actually a ceramic binder, templates, all of that jazz, all of that in here right now. So I'll pass some of this around. And what we do is we actually then take this and we cut and stack it. And don't worry if it rips or anything. So then for the next step, we cut and we stack this so that we can align these seeds in this direction here. So going up, we have alignment going this way. Other than stacking it, we can also cut it and do something like wrap it around a mandrel. This gives us another geometry that we can't do, with like single crystal. If you were to do this with single crystal, you can't grow it in this direction. So it actually opens up things that single crystal cannot. And then once we do this, then we go through typical heat treatments like Angie talked about earlier. Your first step is going to be to heat it up in a BIS cycle and heat out your binders, any water that's in there. And then really your second step is going to be this sintering phase, which is your high temperature sintering. And what I've shown here is this is a sample that hasn't been sintered very long. It's one of these where, we've taken it, we've broken it in half, put it in the SEM, and then this is a sample that's been sintered, to completion. And what you can see here is here's your seeds, they're aligned, and growing around it, here's your ceramic material, and it's growing in the same domain structure as your seeded crystals. And really, the best way to track this is powder X-ray diffraction. So since we're looking at something that is preferred orientation, when you look at the X-ray, so this would be random, so you get a random distribution of your X-ray reflections. And then here is something where they're looking at different amounts of seeds here, but what you can see is this is a textured one, and right away, once it's textured, the orientations that were there before from something that's random have disappeared, and you're now looking at all one orientation. And then this is just an example of a structure here. Once it's been heated, we electrode it, we pull, we do everything the same as a typical ceramic, that Angie talked about earlier. Another important step that, is an extra step is we have to grow these template particles. Now, we may only use, less than 5%, but they do need to be in a special, highly anisotropic kind of morphology. And the way we do that is we take kind of an aurevilius phase and we do a molten salt process where this aurevilius phase, it typically always grows as a plate-like structure. Barium titanate itself usually wants to grow in a one-step, solid state reaction as a cube. So we use this kind of topotactic kind of reaction series to get our barium titanate, but to keep that plate-like morphology that we have in the first, kind of structure type. And the way we do that is we use a molten salt process. Really, it's just adding salt, sodium chloride, potassium chloride. We like to use eutectics because then you can actually lower your reaction temperature by combining them. Our metal oxides, and then, the reagents will precipitate out as this metal oxide crystals. We use this, it's used in a lot of different things, to kind of target alternate crystal morphologies that we wouldn't be able to otherwise get. So, okay. So this is your textured ceramic manufacturing process I talked about. So how does this fit in with our typical type, ceramic manufacturing? Well, it's really in this first step here. This is where we differ. So for textured manufacturing, you do need an automated tape caster. And this has an automated gap control of your doctor blade. You can control your tape height. And then from there, it goes into another piece of equipment. You transfer your roll, and your roll then cuts your tape into what I've passed around, which is just, and you can peel it from the backing. A shape that you've set, puts it into cassettes. And then from there, it gets peeled off the mylar backing and stacked by another automated piece of equipment. And really, when you start out R&D for this, this is all done by hand for technicians, all the cutting, the peeling, the stacking. So this is really the next step of the process that, we do now is manufacturing. And then from there, it kind of integrates back into our same process. And also, we also utilize things that we have sitting, typically in our ceramic processing factory. So a really important part of all of this is maintaining, a set of key processing indicators. And the way we kind of track that is, powder X-ray diffraction, particle size analyzer, and then, scanning electron microscope. Now, we don't do this for every batch, but as ceramic manufacturing, when you see an issue, you have the tools to look at it, but also, points when you need to look at these things to make sure that the product that you're putting out at the final end stage is, the same each time. So I just wanted to show this here. Angie touched on some of this. So where does textured fit in? So this is actually our process at L3 Harris or Edo Western. And this is kind of how it proceeds. We make our matrix ceramic that we're going to texture similar to every other ceramic. And then it kind of deviates. We send it to tape casting. It gets cut. It gets pressed in our textured ceramic manufacturing center. And then it joins up again. And, it fires exactly the same as our other ceramics. What's really awesome is we're able to maintain these same CPKs as we do for our non-textured ceramics that have been around for, 70 years. So with that, I really didn't want to, talk about too much today. But yeah, that's kind of the next generation of ceramics. And here I've just shown, I can pass this around too. This is a textured. It looks exactly the same. You're not going to know unless you put it in an X-ray or an SEM or, you look at the properties. But that one hasn't been electroded. I just pulled it off the shelf this morning. But so, yeah. Yeah.
So Lindsay, in the texture material, are you using, is it going into the same types of industries and applications, or is it primarily focused on defense?
You know, it's going into the same industry and applications. I think with a lot of new stuff like this, defense adopts it first. And that's you know, where we're going to get our most backing. But certainly, I think in the medical industry, what it opens up is, you know, for like ultrasound that you showed, that's primarily single crystal. And textured has these, you know, improved properties where I think, you know, it's really going to replace some of that as well and be, you know, a lot cheaper. So yeah, no, certainly, you know, we're targeting other uses as well. Yeah.
So I'm doing tape casting for my own thesis research.
Yeah.
And I've seen a lot of problems with aqueous tape casting. How do you guys get around those issues?
So first off, yes, it's much easier to do non-aqueous, but you know, when we started out, we wanted to tackle aqueous because at the end of the day, we would have to build an entirely different facility, have different ventilation, everything. You know, I think it comes down to, a lot of it comes down to understanding, you know, your viscosity, your rheology of, you know, what you have in there, particle sizes. There's a lot in there. So definitely, and you know, it's not cut and dry when you say, oh, we'll just increase the doctor blade and we'll get a thicker tape. That's not quite how that works. So yes, there are some obstacles, but I think early on, I think it's good to struggle with it because I think, you know, this is something that is more easily adopted than having, you know, to put all this new ventilation in. And aqueous it's more difficult. It is. You know, and you hit pH effects. There are so many things that you have to think of. So definitely, you know, and then recognize what are your key performance indicators in developing your slurry for tape casting, you know, that you need to maintain and where you need to characterize. So yeah, all of those things, yes, I definitely understand. So, yes?
You mentioned that to grow the barium titanate, you're using a topotactic crystal growth process. Is that to force it into that platelet as well?
Right. So the auruvillous phase, the first one, always grows in a plate-like morphology. That's just how it likes to be. So what we do is then we, you know, substitute different ions in, you know, change a little so that we maintain that plate as we get to barium titanate. Because barium titanate on its own is just going to want to be a cube. Or, you know, yeah. So that's why we use that process. So yeah, there's definitely that. So, yeah.
I have a question for Angie, if that's okay. You were talking about how the perovskite ceramic can be used in ultrasound applications. How does that relate to the ultrasound techniques and stuff? Why is the perovskite ideal for that?
So I think that from an ultrasound perspective, we have a couple. So ultrasound being single crystal. If it's single crystal, it's typically more of a lead, magnesium, niobate-lead titanate composition that is then grown because of the difficulty of, I don't even know if anybody has done single crystal, PCT. So it is PMN-PT composition. But some of the ultrasounds are still perovskite PCT compositions. It kind of just depends on what the customer is willing to pay in terms of unit cost. Hopefully that answers your question.
The ceramics that were being passed around were quite large. Now, both of you kind of said that these are using like small electrical devices. Do those larger ceramics have any use, or like what are they used in?
Send around, a lot of the stuff we do is small. It's just,
So certainly the larger the that we were probably passing around was probably for the defense industry. When you're out there in the ocean, you want a lower frequency in the 2 to probably the 2 to 10 kilohertz range, so that you can travel farther distances. So almost all of those bigger pieces are that we passed around were that. Now there were some ceramics that were blocks, like kind of a rectangular block. In those pieces are typically cut into smaller shapes. So it's formed, because of economics, it's formed in a larger block and then cut into small pieces.
We call this grind stock.
Prior to sintering, with the mixing and crushing and the pressing of the material, is it piezoelectric at that point? And if so, do you have to worry about electrical discharge by putting pressure on the different phases?
So technically it is piezo at that point, but not an active piezo. So it hasn't been polarized, so it has really no charge associated with it, and so there is no risk at touching it. It's only until you basically align those dipoles and put an electrode on either surface that you can then you become the path, and that's where you get your little sparks. Questions though?
Kind of a silly question. How many sheets did it take for that one you passed around that was actually?
For that one, I want to say that was like, but that one's actually been ground down a little. But yeah, it's and that's why it's important to have the automated equipment. But starting out in R&D, in a technician and a PO instead. So yeah. Yes.
So notice with those sheets, you get quite a bit of a warping effect, especially in tape casting. Does that affect the final properties of the piezoelectric?
What effect did you say?
The warping effect you get when you get the sheets?
No, usually, so what I forgot to point out on the last slide is we actually don't get that. I can't give too much information about the orientation or some of the process stuff that we do to minimize that effect, because if you were to position them all the same, you might get that. But for the tubes, what we do is we do kind of a two-step pressing process. First, we do just a light tack, and then your actual part that goes into an isostatic press.
Okay.
But no, usually we don't, and there's ways to kind of work around it. But yeah, definitely good question.
Can you mention a little bit about the chemistry control to get high dielectric? It seems like that occurs at phase boundaries, and is this stuff that is difficult to control, or is it easy to control, or what can you tell us, and how proprietary is that information? And you probably easier to talk about, so you have any proprietary.
I think, because I'm sure Lindsay would say that every individual manufacturer is very concerned about proprietary formulations and would not be willing to share that with a broad audience. As far as controls for dielectric, it is within a wide window. You can, so let's say a wide window being plus or minus 15–20%. It's easy to hit that target. When you're restricted down to a wish list of maybe plus or minus 5%, it becomes very difficult in terms of repeatability. And I think the key there really is that if you change your source of supply, if you were forced to do that, or you elected to do that, that could totally affect that performance. And so you may have to adjust chemistry, you may have to adjust process to zero in on that value.
But can you talk about when you think the Salt Lake facility will be lead-free, or will it never be lead-free?
I don't think, well, I don't think it'll ever be completely lead-free. We offered lead-free formulations from the Western facility.
products that it goes in that, you know, are going to be around for a long time, especially military products where, you know, they use this, you know, for 20 more years.
You've got a specification.
Right, exactly. Now, I will say that there are some obstacles to having lead-free and lead-based products. You know, lead oxide, it's pretty volatile at a considerably low temperature, you know, about 950. You know, but we're careful to separate all of that. But that is an obstacle that some people see is, can you do lead and lead-free in the same facility? And yes, we do have to do certain controls. But I don't see.
And because of the, but because of the defense industry, there's been an exception for a long time in terms of using lead-based materials. Will that go away? I think that there certainly is a push to do that, but in the course of national security, we're not going to do that, probably in my lifetime. Let's put it that way.
I don't think mine
Are you going to do anything with the new Scandia built aluminum nitride or with the actually built zirconia materials? Are they things that you're looking at?
You know, I think why I like working at the Idaho facility is that, you know, we are able to do a lot of R&D and look at, you know, a lot of things that start out in academia. And that's why I really do my job. I get to do the manufacturing, but I also get to do all the research.
Let's give a big round of applause.